So, hello again. Now we'll have Guillaume Binet that's going to talk to us about copper-RS, open source, something for robotics. Awesome.
So thank you so much, and welcome everyone. Welcome on the stream too. So yeah, I'm Guillaume. I'm the author of like a copper-RS, like a Rust engine for robotics. So probably most of you read that and say, oh yeah, another dude that just like took something, rewrote it in Rust. Oh, come on, another spin of it. No, give me a chance. So, yeah, that doesn't work. Right, so a software engine for robots. I have a good way of kind of having a ground comparison of what happened in another industry, which is the gaming industry. Hang with me. So for those old enough to remember, okay, who knows what's the game on the left-hand side? Wow, nice! Oh my God, like the geekdom is here. Prince of Persia. That's the dude. I don't remember his name actually. Took his son with like a roto frame thing to actually make the animations of his game. Everything was encoded with assembly language, and it was amazing. Like back then, you look at that on I don't know, an Amiga or Apple II. It was absolutely incredible. It completely changed the way you see animations in the game and so on. But something was like striking. It's like everything was really encoded for that game. That nothing was ever reused from that implementation. But something happened in the 90s. So probably everybody knows this one in the middle. And this one has been ported on every single platforms ever. That's Doom. Right? Doom basically created what we call now a game engine. And they realized something back then when they make that engine is that a little bit like on a robot, you don't, I mean, people working on a code base and assets of a game, they are not coming from the same place. Some of them are, hardcore developers that are making algorithms, but you have like people specialized in sound, people specialized in 3D, graphics, and so on. Like in robotics, you have people that are coming from mechanical engineering, or like controls, or like physics and EE, and so you have a lot of people that are actually working around a robot. And the industry kind of matured from that point on. And you have like all the games today, like AAA games, you see like full studios of people that, just have like a specific view of their own games or their own like development or contributions to the game depending on where they are coming from. And you see all those amazing games you have today. So Copper took that page out of that story and really try to, really from scratch, like 2 years ago, when I spent like 10 years really trying to support like robotics engineers or roboticists, trying to think what would be the best tool today so those people can all work together on a robot efficiently and not shooting themselves in the foot in the process. So what's wrong with ROS? That's going to be my first question for that you would ask. Things like ROS is amazing in its. I mean, I've seen so many students going to, I don't know, University of Austin or other universities, CMU and so on. I look at what they can do with like so little, just few Python scripts scrapped together. They have like they have their components. They can actually log on their system. But it has like serious flaws for me when you try to get that from like a prototype to an actual product. It's actually fighting you a lot. One of the key reasons is it is completely asynchronous. So people are going to that way because they think like, you have like a big, I don't know, multi-threaded machine with GPUs and so on. So asynchronicity is good. Like you have an event and then it answers to that event. So you try to optimize that aspect of the robot. The huge issue with asynchronicity like it is done on ROS, it is non-deterministic. So what I say by non-deterministic is that you grab your ROS bags, you log them on your robot, but you never have any guarantees that when you get back your ROS bags and you try to replay your code, that your code's going to replay the same thing as what happened on the robot. And that has like a lot of like a kind of like cascading consequences when you are trying to make, for example, like autonomous robots, like things that needs to be safe, and where also you have like a lot of people working on that needs to reproduce a lot of cases out of your robot that they either encounter in the wild or in simulation. There is also the C++ situation. I mean, I spent literally nights on the passenger side of a self-driving car, wondering what the hell is going on with this code base. Everything passed, like all the linters passed, and I remember one that was very serious where I had like some kind of like, it was so strange. The perception system was actually less performant than it was supposed to be, and it was a corruption that was at the limit of our user code and the TensorRT layer, and that was a stupid for loop that somebody did where there was like an undefined behavior, and you look seriously like a lot of people had their eyes on this thing, and it went through all the way through the car. So C++, again, think about like what I said about the game engines. People are like roboticists. Usually they see really C++ as a tool, like a screwdriver. They don't care. They don't care. They don't care about like complexity of the language and so on. They want something that is safe to run and to implement what they have in mind, which is usually math. Usually those are like pure transforms for your robots, for any algorithms, including machine learning. And yeah, C++ doesn't help there. And the thing also is that people often switch back to Python then, because Python is actually safe. It's hard to actually crash Python, and it's easy to use. And then you have like situations where, you have a management on your back saying you need a robot that needs to go to production, like half the code is in Python, and you're like, no, it doesn't even keep real time. It cools in the lab, not really on the public roads. Performance is horrible. It's just terrible. You'll see with Copper. I think the comparison is more about like ROS being slow than actually Copper being fast. Also, the fact is it's really dependent on your system. People try to port ROS to various systems. I have it on my Arch Linux. It's terrible because like you have like so many system dependencies and package dependencies out of the systems. That's something also that really hinders people to actually have a system that is reliably in production where you can update it and put it in the wild. Like you'll see also on the safety. So, okay, I talked a lot about games, about ROS. Let's look at Copper. So Copper is, when I really started it from scratch, the non-negotiable first principle I wanted to implement in there was determinism. So to be sure that what you run, so literally you run, let's say, something in simulation even with Copper. You can try it actually on the repo. You run your robot on simulation, it logs the robot. You strip out the outputs. You rerun, not the product, but you replay basically with Copper that log. You compare the binaries of the two logs. They are exactly the same. So think about it. For a roboticist, it means that those logs, you can put them in the cloud, and you can be sure that when your test case passes, it will always pass. And when it doesn't pass, you know that you regress somewhere. So it's also designed for safety. Conceptually, actually, Copper is a lot of things. One, it's a compiler. Basically, Copper extends with macros in Rust, the Rust compiler to actually create your runtime. We don't depend on anything so much that you could say that Copper is an actual operating system. You say ROS is an operating system. It's not. That is an operating system. I have a file system, I have a scheduler, and I run like bare metal. You can run on STM32 if you want, but it runs of course on standard process, real-time Linux and so on. But you can also run it like a bare metal because I depend on nothing. It's very performant, like high bandwidth, low latency. We are like out of the box. If you want to do, I have some examples in the repo. If you want to do the same chain of tasks that you run and log for each of them, for the latency, I'm 100x faster than ROS. So that's 100x. Yeah, because like it generates basically the operating system to run your robot. You design your robot, you say to Copper what you want to run, and it accommodates you the system around the architecture of your robot. So it's very hard to beat. I mean, it tries to chain up like all the tasks back to back in memory data with like a data architecture. So it's always like hitting all the caches and linearity of all your systems. Same thing for logging actually. Logging, we log. We don't log like ROS bags are kind of like indexed and all over the place on an hard drive. We log so linearly that we don't need a file system. So you give it a partition and linearly it will log back to back, back to back, back to back. So for an NVMe, for example, it's the difference between 7 gigabytes per second to something that is 500 megabytes or 600 megabytes per second. That's the difference of a successful product or not. Because if you want to match that performance, you need 10 times more like NVMEs. How do I know? Actually, architecture self-driving cars were hard to put like arrays of NVMEs where I was like, what the hell are we doing? And the jitter also is important, something that you realize quickly with robots. In a controlled environment, your robot will run like nicely, but suddenly you have more people or more objects around your thing, and if your own system adds some noise into the measurement, you don't know in terms of performance, like, okay, what triggers that kind of like a randomness into the execution of your robot. So all in all, that allows people to focus on algorithms and not all the details I told you. Copper does that for you at compile time. Should we try a demo? Can you make a prayer to the demo gods? So that's on the repo. You can actually try it yourself. And one thing I tried really hard to do is that, you know what? That's just a Rust app. You don't have Colcon or things or special makes files or whatever. Cargo run. That's it. That's my non-negotiable. You clone cargo run and it should run-ish. Maybe. So come on. Oh, no. Yeah. Yes. Maybe. I'll make it happen. Here we go. So that's a very simple robot, which is just like a self-balancing rod. I do that because I don't want to explain to you a robot. So everybody knows this example. Actually, I don't see my cursor, but I'll try to show you. So that's just a self-balancing rod, like in a rod in a simulator. I do have the actual robot at home. It runs exactly the same code. I cannot really see what I'm doing, but so you see. So that's basically Bevy. Bevy is like a game engine in Copper, but we do support like various like simulators. That's just one that is easy because of this Copper run. Like that's like a Rust dependency, so I can run it straight away. You can see a little bit like the console. There is a console like to monitor real time what is happening on the robot. So it shows you here the structure of the robot itself. So that's a big config file that is modular. You can add that. So the big difference between ROS and Copper is that you actually define your robot ahead of time. So you say what's going to be connected to what and who is sending a message to what. That's part of the determinism aspect of it. But it still have the same concept. You have a task, you have input, outputs, and you talk like you kind of send messages, even if we don't really send messages in that example. And you can visualize that they are like this little like kind of DAG, where you have on the left-hand side sensors. This is Raspberry Pi running. Like some algorithms, the PIDs, it's really simple, and the actual output on the right-hand side. So this thing also, when you look at the latency, so you have some zeros because some of them are actually simulated. The other ones are actually executed. So I give you the number on the simulator there, but you will have the same thing on the robot. You see, I mean, that's a small laptop. It's measured in microseconds, and if I run that on my desktop, it's gonna be nanoseconds between. Basically, sometimes it's zero because with the superscalar features of the CPU, you can have actually data that is going so fast that we measure twice the same timestamp on the CPU clock. So, and I'm talking like that, but you would say like, why do you need nanoseconds of latency? But think about it, like when you have a good logger, like we have, and a low latency, suddenly you can think about your robot and actually subdivide your robot with like blocks that are as small as possible. So it gives you visibility on every single blocks, input, output, input, output, input, output, and basically for free. So you can, I don't know, you can put like 10, 12 layers of blocks like that, and you have like, I don't know, 1 microsecond of latency end-to-end, if it is pure CPU. That's pretty cool. I mean, overhead on top of what you're doing, of course. If you're spending 3 seconds on your task, it will show. In terms of bandwidth, so that's capped to the simulator, like 60 frames per second, something. Like that's where you can see what's the efficiency of the logging, what's the bandwidth you use. Because often, like what happens when you are building a robot, you hit like limits on your system that are actually not CPUs. They are either I/O or memory bandwidth often, because you are dragging like images or LiDAR points, like super heavy things. That's why I really wanted to have that view where roboticists can show like, oh wait, I just added like a camera or like a new LiDAR. What's going to be the cost in terms of performance? And yeah, that's pretty it. I can show you something. I have 7 minutes, so I try to can show you quickly how it looks like. So you define your tasks on that's the one you saw on the little graph, and just like you tell it basically an ID, so you can connect them and refer to them in the logs. You give them a type that is kind of it's just like a Rust type that implements like few threads depending on what type of component you are building. Yeah, you can give it like those ones are like hardware configurations. Those are tuning for PIDs, so it's pretty self-explanatory. And you connect them. So basically you say, oh, I want to connect this source with this destination with this message. It's very simple. Yeah, let's go back to the presentation. So yeah, I want to be sure that you have some time for questions, because usually I trigger a lot of questions out of that presentation. So I would like to thank the amazing community. I have like a bunch of contributors now on Copper, and yeah, we really we are moving forward a lot. We just we integrate like this bunch of like either middleware like Zeno or Isorix. We do integrate with like CV algorithms like Cornia. We have like Hugging Face and Fire and Algebra, the algebraic like systems on Rust. So it's really Copper is one thing that is actually gluing together a little bit all that Rust community of like in robotics that is actually going and reinventing a little bit like what I did with copper. A lot of things are actually not just rewrote in Rust, but actually reinvented in Rust. And that's pretty amazing. I'm super happy to be part of that ecosystem. Of course, like the two ones at the bottom, we talked about like rerun and FOSDEM. So FOSDEM is more like you saw that before, like a visualizer. Rerun has also like an amazing integration with Copper because it integrates of course, at the Rust level, at the API level. So it's with 2 lines of code, you can actually show what's going on in rerun what's going on in Copper with rerun. One small ask, if you like what I'm doing, you're supporting the project, yeah, please, a star on the GitHub repo would be amazing. Thank you.
First, thank you very much. That's a lot of work, and I appreciate that. How does this framework interact with other programming languages, in particular Python, which is taking over robotics with all the machine learning approaches? Yeah. Which in the end is calling C++ and Rust, I know, but how does it interact?
Yeah, no, good question. So we do have already a Python API, but for the logs, because for example, you don't want to do data analytics in Rust, I tell you. So our logging is actually an API. And so we can use that to export that to other systems, like we said for Xlove. But also you can get that and get straight, like you get your robot, you can have your IPython worksheet, and you can actually get the data straight out of a Python interface.
Live too? Live data too?
The what?
Live data too? Like in the
live
topics, looking at
live data, you could do it. We don't support it yet, but we could. So we do have like what we call like bridges also, where you can integrate with your Python code. We use Zeno, for example, for that, where you can actually like submit data to a channel, and you have bindings for those like types in Python. So you can do that like remotely. What we haven't done yet is actually enabling Python itself in the tasks of the robot. It's not hard to do. Like there are like tooling in Rust that is doing that very nicely, but I'm a little bit scared because like then you have like the little bit the Dora situation where a lot of like people contribute just Python. While I really, especially where I am in the community today, I really want like solid like building blocks for basic things like drivers or like, I don't know, ICP and those kind of like simple things that I really want to be nailed. At some point, I will implement like a first-class Python support for sure.
So you have bridges, like let's say we have our system, we want to migrate towards your system, so we start with whatever we have. I'm going to say Rust because that's what I know. And we want to migrate some elements to your OS. Do you have bridges set up so you can communicate? Yeah.
So we do have a translation layer for Rust 2, so you can also talk to Rust 2, so that's also one of your escape hatch from Rust.
Thank you so much for the talk. Really cool concepts, and I think that Ross could learn a lot from that. But there's a thing on your website that you say that you have a patent on copper. Could you clarify that?
Actually, I let it expire. So I had a provisionary patent on it, and it's not valid anymore.
What's going to happen?
It's not patented at all right now.
What's going to happen with that? Because I'm not even going to touch software that's patented.
It's not patented actually. So
okay.
It was a preliminary patent, so basically it's not a patent. Just like saying maybe I would patent it, and I decided to not.
Okay, it would be good if you updated the website because for me it was like quite scary.
I'm
not going to touch this. Yeah. Okay, cool. Thank you.
We might have time for one more.
Hey Guillaume. My question is if you have a system that's built on Rust 2 already, what is the migration path? I really like what you're doing.
Yeah.
Like I don't understand. Like, do we have to start from scratch and rebuild everything? They're like.
Very good questions. So we have a system, and one of our users is doing that actually. And what I recommend usually is so we have a bridge between Copper and Rust 2. And so you can send messages from one to another. So your copper system can act as like a big